All right, so what this is showing is, and so as Thai said, this current carrying loop is an electromagnet. Okay, so what this formula gives you is the following. So let me do a drawing. Let's go to the chalkboard. All right, so what this chapter is about is a current produces a magnetic field. So here's a current. Okay, so we know that this is producing a magnetic field. It's producing a magnetic field everywhere in space, all the way to infinity. And the further out you are, the weaker the field gets, okay? Now, if you ask me what is the current magnetic field at this location, well, I can't give you the, I can show you pictures, but I can't give you the exact value for it, okay? What one can do is, if you ask the question, what is the magnitude of the magnetic field along the axial point, along an axial point, we can do that for you, okay? So if R is the radius and this distance is Z, okay, that's what this formula gives you, okay? So mu naught is a constant, as we know. N is the number of turns in this loop. Right now, there's only one loop and one turn in this loop. But if you wanted a strong magnetic field, if you wanted a strong electromagnet, all you do is wind many turns of a wire. So you want a strong electromagnet, you just take a whole bunch of turns, okay? And that's what N is. I is the current. You want a strong magnet, pass a stronger current. R is the radius of the loop, okay? And Z is the distance along the axial point that we talked about, okay? So Z is the distance along the axial point, okay? So the magnetic field along the axial points are given by this formula, okay? So if Z were 0, for instance, if Z were 0, so mu naught NR. Okay, so the magnetic field is given by mu naught N I R 2 R squared plus Z squared 3/2. So for this point, for Z equal to 0, this would be R to the power of 3/2 to the power 2 to the power 3/2 would be R cubed, and that would be R squared. So it would be this must be R squared, N I R squared 2 R cubed 2R. Okay, so at this location, that's the magnitude of the magnetic field. Okay, so that's what that formula gives you. It gives you the magnetic field along the axial points. Okay, and for points very far away, large compared to the radius of the loop, it turns out that for points large compared to the radius, you can ignore that. And this becomes Z cubed, okay? So it becomes, goes off as Z cubed, and mu is the magnetic moment of this current loop, which is related to the area. It's NIA, the area of the loop, okay? That's the magnetic moment. All right, so that's what this tells you. So this is showing you a graph of the strength of the magnetic field along axial points, okay? So again, what that graph shows you is the following. So here's the loop, and it's plotting B. Now here they're calling it X, B as a function of X. Okay. And at the center of the loop, where X is 0, that the magnetic field is strongest, and then it falls off as X1 over X cubed. Yeah. All right, Now, this is a slightly different topic. Okay. Now, before I get into this, before I explain this, let's go to the chalkboard and remind you of a couple of things. You saw that this is from last chapter. So the fundamental relationship was if you have a charge moving in the presence of a magnetic field, it feels a force. Okay, so what this equation is telling you is a charge moving in the presence of a magnetic field feels this force. Okay. So again, there's a lot of symmetry to physics laws. Moving charges, remember, moving charges produce magnetic fields. Moving charges, they produce magnetic fields, and magnetic fields influence moving charges. Okay. Right, so anyway, that's just an aside. Okay, so what this equation is telling you is a charge moving in the presence of a magnetic field feels this force. Okay, so here's a current. Okay, current is a bunch of moving charges, and if you have a current carrying conductor in the presence of a magnetic field, it feels a force, and we saw this last chapter. And if you use your right hand rule, I cross B, I turn to B, it would, the force would be in this direction on this conductor. Okay. Now in this chapter, what you learned was if you have a current carrying conductor, it produces a magnetic field. So this current carrying conductor, again, stick your thumb out in the direction of the current, and it tells you this guy produces a magnetic field out of the sheet here and into the sheet there. Okay, so again, all right, so here are two independent pieces of information. Current carrying conductor produces a magnetic field around it. And if you have if you have a current carrying conductor in a magnetic field, it feels a force. Okay. So now what we'll do is the following. Okay, so here's a current carrying conductor, it produces this magnetic field. Now we'll put another conductor in this magnetic field. And this guy, I cross B, will feel a force in this direction. Okay, so what's happening here is this current produced this magnetic field, and this current in the presence of this magnetic field felt this force. Okay, so that was what was happening. And what you can do is you can keep it simple and say, hey, to a little kid, what you can say is, hey, look, two parallel currents attract each other. Okay, and you can do a similar analysis. And what you find is if currents are moving in the opposite direction, they will repel each other. All right, so that's what we're going to see. Two parallel wires carrying steady currents exert forces on each other. And you saw how that happens. Okay. So the force per unit length of the wire, is given by mu naught vacuum permeability times the product of the currents divided by 2 pi times A, the distance between the wires. Okay, so the force gets weaker the further apart they are. And notice something, even if one of the currents is 0, the force is 0. Okay. So for an attractive or repulsive force to occur between the two wires, they both have to carry currents. So parallel currents are attractive and anti-parallel currents are repulsive. So let me show you a little simulation. Okay, so here's you see, if there is current in only one of the wires, there's no force between them. And of course, if both currents are 0, there won't be any force between them. If the two currents are in the same direction, there's an attractive force between them. This guy is attracting him, and what is this guy doing to him? Anybody? What is this guy doing to him? My Newton's third law, if this guy attracts him, this guy will attract him in return with the same magnitude. And if the forces are, if the currents are anti-parallel, they repel each other. So this guy is repelling him, and this guy will repel him. Okay. All right, current carrying conductors, when they're close to each other, they interact, okay? And they exert a force on each other, okay? All right, so now here's a slightly different topic. So what I'll do is actually, I'll pause.